X. We've got the triangle. The thing to keep in mind is when we have this X, we're looking at it piece by piece as we go along. And when you have a triangle like this, if you're looking at this part of the triangle, this is different from this. So we need to account for that. And we account for that using the law of proportionality, I think it's called. I forget exactly. But it basically states that if you have two triangles, and you have one inside of another, and they have all the same angles and everything, that there'll be a ratio between lengths, which would be, you have A being this, and big A being that. This is little b, this is big B. A over B will be equal to little a over little b. So, for our intents and purposes, we have X, and we have 12. Here we have 3, and this will be Y. So we have 12 over 3 is equal to X over Y. Solving for this, we get that Y, putting it over there, is equal to X over 4. So this is X divided by 4 for our free body diagram of second with the first 12 feet of the second. And when we take this, when we solve for the shear that's happening right here, the moment happening here, we still need to consolidate this force. So we'll still have the 10 up. We'll have something. We have right here the shear. We have the moment. And we need to consolidate this. So the first thing we can look at is it should be 1/3 from the big end or 2/3 from the small. But we're evaluating everything on this side, so we want to know what this distance is. And that's just 1/3 from the large end. So it would be 1/3 times X is this distance. And the magnitude is 1/2 the base X times the height, which is X over 4, and that gives us X squared over 8 is consolidated force. Now we can sum the forces in the y direction, and that will be V plus X squared over 8 is equal to 10. And we'll sum the moments. And that will be moment plus X squared over 8 times X over 3 minus 10X. Moment plus X over 24 is equal to minus 10X is equal to 0. Those are our two equations for up to 12. And then, like I mentioned before, when we analyze the last piece, we don't really want to look at the whole thing because that would be really complicated. Instead, we will just look at the other side. So we will go from this by to this point, which will be 12 is less than or equal to X is less than 18. And right here we have the shear, and we have the moment. Because we cut this through the middle, right there, our shear and our moment have to be the opposite of what we treated them as right here, just because equilibrium states that they need to all cancel out. That's all we really have going on at this point. So we can sum the forces in the y direction. We just end up with P plus Py. P will be equal to -10. And we have the moment. The moment is equal to to y, which should be 18 minus x. And it's 18 minus x because we are going from 12 to 18, so we need to keep this, like this distance is 18 minus x. This will be 6, and 5, and 4. If they're 3, 4 is stacked. I'm going to construct graphs. You will have graphing calculators. I recommend using them to do this because, well, I mean, if you can do those graphs, you're going to have to impressed. But as you kind of do with anything, you plug in your 0, you plug in your max and find out. I just remember the graph. It starts right here. It goes down kind of like this. And when you plot these 2 points, you realize you are crossing the x-intercept, so you do have a 0 point. And to find that, you would just plug in v as 0 and solve. And that gives you something like 8.94 feet is where this point is. And then the rest of your graph, we have the v is equal to -10, which makes sense. That is where we end up. So you just come straight until you hit the end of it. And it comes up and connects with the graph and all that is straight. And then we have our moment graph. And for this one, you plug in 0, you get 0. We end somewhere over here. But we know that we have an inflection point right there. So we'll plug 8.941 or 8.94 into the moment equation in the first part to find out what the maximum is up here. And then just graph it. And our moment equation at the end is linear. So it just goes down to 0, kind of like that. And I guess keep the answer. That's pretty much how you do these kinds of problems. Again, the important thing is usually being able to find what the maximum is or what the moment at various points are.
Can you scroll up a little bit?
Sure. Does anybody have any questions about that?
What's that one line there, second from the bottom?
I'll just erase my work.
No, on your work there.
Oh, this one?
Yeah.
This is the sum of the forces in the y direction.
What you have written there, v plus by?
That's all it is. It's just v plus by.
Okay.
It's the only 2 forces. And then I plugged in the 10 and I moved it over here. V is equal to -10. It's writing too fast. Is everybody good if I erase that? Start copying. So erase it. Those done. We're going to do the problems of these equations I wrote on the board to start the class. Or restart. You guys have gone over this in class, right? We at least recognize this as a format of the question. The equations, I hope. Okay. So they want the moment to find the moment that creates a maximum stress of 10 psi on the cross beam. So what they tell us is that stress max is equal to 10 KSI. You know that the equation for it is right here. So we just need to solve, we're looking for this, we need to find out what our C is, we need to find out what our I is. C is the distance from the neutral axis to whatever point we're analyzing. In this case, we'll be analyzing the top and the bottom of the shape to find out where, or what the maximum moment is. So that's not symmetrical in two ways, it's only symmetrical in half. So we'll need to use Y bar, and we'll start there because it's a little bit easier. On this shape, I'm going to choose various pieces. This is going to be number 1, these are going to be 2, and this is going to be 3. When we do this, we take, I forget what the term for this is. I think it's a neutral axis of the shape. I forget. But times the area divided by the sum of the area. So for shape 1, that is, I'm treating my 0 as this point here. You can treat either side, it won't make a difference in your answer as long as you're consistent. But for this problem, I'm going to start right here. It seems a little bit easier. And it would be at about 0.25 inches, because that's the midpoint of shape 1. While the area is 0.5 times 4. For 2, the midpoint is 1.5 on the shape, but we are half an inch down from where I treated as the 0 axis. So in this case, it's going to be 2. And the area is 3 times 0.5. And for 3 is 10 inches, but again, we're 0.5 down from where we started. So that's 5.5 inches. And the area is 10 inches times half an inch. Now that we have all this, we solve for Y bar. And we'll have 0.25, 0.5. 4. And we have 2 of shape 2's. I'm going to multiply it by 2 rather than y squared twice. 2 inches times 3 inches, 5 inches, plus shape 3, 5 times 10 times 0.5. This is all divided by the areas of each shape. 0.5 times 4. 3, 0.5 times 10 times 0.5.
So it's 1 over you're divided by the area of each shape. What is the numerator?
The numerator? It's the midpoint of each shape times the area of each shape. But you got to remember that the midpoint is in reference to wherever you're treating as 0.
Okay.
So you would treat like the top of the shape, or the middle, or the bottom of the shape as like your 0 axis. But it doesn't really matter which one you do, because it will always give the same Y bar.
Okay.
If it doesn't, there's some mistake going on somewhere. And I don't remember what the answer is, so I gotta look at the solution real quick. This one. That's 91.73.
That
Well, that's I, sorry.
3.4.
Yeah. So y bar should always be on the shape somewhere. For the purpose of this class, it should be on the shape. So,
On the bottom, shouldn't the summation of the areas not the, you have them multiplied together?
I do, sorry. That does. Now that we have y bar, you defined I. And kind of like with this, you basically add each component together. So for I, it's going to be 1/12, and then each shape. So we'll start with number 1. The base is 3 inches times 0.5 cubed plus 1/12. I'm going to make this 2/12 because it's 2 number 2's. The base is 0.5. And the height is 3 cubed plus 1/12. 0.5. Base times 10 cubed. And this one should be the 91.
So you're doing 1/12 times base times height cubed?
Yes. Because that is the equation for I. When you have that's this is the format you use when it's a symmetrical shape. But we don't have a symmetrical shape. So what we need to use is the parallel axis theorem. Which is fundamentally the same equation. You just have a little bit added on to the end, which is the a d squared. Where d is the distance of that shape to the actual parallel axis. And it's just easy to show this a little bit. So it's pretty much all the same. So we have 1/12 the base, the height cubed, but then plus the area, which is a 4 times 0.5, and the distance from the neutral axis, which is the 3.4 that we found over there, y bar minus the 0.25, which is where the neutral axis of this shape is. And you do that for each piece. So this is 1. This is here is for piece 2 multiplied by 2. And this is for piece 3. And you know you need to use parallel axis theorem because you use it every single time you have to find y bar because the shape's not symmetrical. And that'll give us 91.73. Does anybody have any questions about parallel axis theorem? Well, once we have all these, we can fill out our equation. We've got the 10. We have the moment. We have 91.73. However, we need to find the maximum moment. In the maximum moment, we have y bar, so we know where the middle point is. And we need to go from there to the top and from there to the bottom. So we will have to evaluate this twice. We're going to do it once, just at the 3.4. And then we're going to do it again at 10.5 minus 3.4 divided by 91.73. When we do that, if you want to do it proper, you do it both ways, but kind of by inspection you can tell that the greatest moment will be at the farthest point, so you don't really need to just use 3.4.
Where are we pulling this 10.5 from?
That's the height of the full shape.
The 5.
You see this diagram right here is kind of showing this is where y bar is. So we evaluate this segment right here and this segment right here, but because this segment's bigger, the moment's going to be larger down here.
Okay.
Any questions?
Max stress is stable.
Yes, it is 10 KSI. And the equation for stress there is the flexure form. Which is what the prison Soltani looks like it should be on.
Oh, this is one.
He sent out a video that was on the flexure formula,
Yep.
and that's what this equation is, so this should be the kind of stuff that you'll see tomorrow on the quiz. I've got more of these to do, of course. I'm just saying that's...
Yeah. There you go. Looks like.
If anybody doesn't stop me, I'm going to start a race. Also, please be sure that everybody signs in on the attendance sheet.
What's that?
I don't know. This is a similar problem. Where do we start? Anybody? Looking at this shape, it's symmetrical in two ways, which means y bar is going to be in the middle of it. You don't have to bother calculating this. You can, but all it will tell you is that it's dead center. Which is great, because that means we don't have to use parallel axis theory. So we have a moment, one kick foot. And they want stress max. And they also want a three-dimensional view of the stress distribution acting over the cross-section. And what they mean by that is, I can't draw. It's a diagram in the book that has the 3D image of the forces coming out. It's triangle-shaped. Basically what they're talking about. The solution will have a nice picture. I can't draw the same line, so I'm not going to try. Now for this problem, what do we do? We already said that we know y bar, dead stop, dead center. Yeah, they gave it to us. Yeah, we know that. So all we really need to do is calculate R, because that's the only piece we'll need for this. We know that y bar is in the middle, so our C is going to be the same whichever way you go. So we just do I is equal to, and there's two ways to do this. There's not really an I equation for an I beam like this. It's only for squares, or circles, or triangles. And you can treat this as one big square and subtract the open parts, or you could do it as three small squares. I prefer to do it as a big shape and subtract. It's a little easier for me conceptually, but whatever works best for you. We have, doing it that way, we'll have 1/12 the base, which is 6, and the height, which is 12, 15. And then we'll subtract these sections. And looking at this is 6, this is 1. So the base of the open sections is 5 in total. So we'll have 1/12 times 5. And then the height of those sections is 12. It's 12 to the third. And that'll give us I. And we know the moment. And C will be 7.5. And at that point, just plug everything into your calculator. If you haven't done this problem.
Oh, okay. So you're just going to write down.
Oh. Problem?
Perfect looking at you, right?
Okay.
That's it.
Yeah. You see? That's fun. They do the same thing. You do it that way. And then you just plug your values in to get PSI. They do it in PSI just because the answer would be 0.093 KSI if you selected that. It's just unit conversion, it's not a big deal. And in this problem, and in a lot of these problems, they keep doing this, I don't really know why. They find the stress at point C, and that stress is right here, where the boards meet. The question didn't ask you to find that, they just wanted the maximum bending stress. But there are other problems to find it. And it basically just is showing that you can change, if you change what the C right here is, that gives you the stress at that point on the shape. And I'm going to scroll down just a little bit to show this diagram, because we have to do a sketch. And that's what the diagrams look like. I hope you've seen it in class a few times, maybe in the book too, if you read the book.
Where do you see it?
That's just something they did. They treat C as the point where the boards meet right here. That's, like I said, not something they actually ask you to find in the equation. Or in the problem. Some other problems ask you to do that. Oh, this one? This C? It was just the middle. Because it was symmetrical. Both, like if you fold it in half this way and this way, it was the same. And that means that the Y bar would be right in the middle. Any other questions?
While you're erasing, can you just scroll it down to see it?
And that's all of it.
Okay, that's all of it.
Yeah. That's a pretty simple problem, actually. Good. This next problem, it's similar, quite a bit. Anybody want to take a shot? Or should I just go through it?
This one is the place for the bed.
Yeah, it was.
Yeah. So, can you start by finding the center of the triangle is?
For this problem, I haven't seen the solution. It should be 5.
Yeah.
Just because it's, again, it's symmetrical in both ways kind of thing.
It was the whole outer square minus center square.
Yeah. And that's what you do when you calculate I. Again, you could do it 4 times, or well, technically 2 and just double it. Find out what I is doing each piece individually, but it's a lot easier to do the whole shape, the outer minus the inner. That's 8 times 10 cubed minus 1/12, 6 times 8 cubed. Right, yes. That'll give you your I. And they gave us that N is 10 kip foot. Kind of just like the last problem. We have M. Just look at this I. You know Y bar or C. You just plug all that in, and that'll give you what the max stress is. Go for the solution. Units, yeah. You do need to convert it from feet to inches. That's it.
Can you, yeah, I'll just make sure. Can you just roll so I can see the guy? Question.
Is there a sign-up sheet?
Yeah. Where is the sign sheet? Everybody good from the board? This one's not symmetrical, so we will need to go through the effort of calculating Y bar. And treat the bottom as 0. So I figure I'll do it both ways. And looking for Y bar for the first. That will be 1.5. And the area will be 3 times 1. 2. Will be 3 plus 0.5. The area is 8, 1. And for the third, it will be 6. And 4 by 1. Everybody see where I got those values from? Cool. So once again, we just plug them all in. 5 times 3 times 1. 6 times 4 times 1. 7. Y bar. Once we have that, we'll calculate I. When we calculate I, we're going to have to use the parallel axis theorem again. So, let's account for the value of Y bar. So we get to 3.39. Around. We'll look for there's 1/12. 1/12 the base comes the height of the first piece. Times 2 because it's 2 of them. 1 times 2. Plus the area, 3 times 1. I mean the distance squared. Again, this is the distance from Y bar to the center of that shape. The center of this shape is at 1.5, so 3.39 minus 1.5 squared. And for the second piece, 1/12, the base times the height. this one, from our neutral axis, it's 3.5. So 3.5 minus 3.3 squared. Because this part is squared, it really doesn't matter which order you have the two values in. Standard convention just seems to be putting the bigger one in front, so it's not negative, but it is negative. It won't matter. And for the last piece, once again, base height plus the area times the distance. And we'll give this our I. Once we have our I, we give this a moment with 2kip. We just plug all of that information in, and we solve for the max bending, the max tensile and compressive stress. And as you can kind of see, pretty much every value you put into here comes from this. I do kind of suggest making this. Makes it a little bit easier, a little less of a headache. But you do you. For this problem, they ask for the max tensile and compressive. So we will need to evaluate it on both sides. And the thing to remember is compressive is when it's squished together, tensile is when it's pulled apart. So compressive will be above, and tension will be below, just because that's where I drew this. So for the axis up here, it would have been the same, it just changed how you calculate it. Which will make sense when we scroll backwards. So these two are the answers. And this one right here is compressive. And you know it's compressive because it's the one above our y bar. And this one's tension because it's the part that's below the y bar. Everybody follow that? Concept. And of course, unit conversions, something that we get a lot. Any questions? I'm just going to keep going. Whoever does. I really like these last two. I feel like, especially the last one, will be something that you might have on an exam. Just my opinion, though. You're wrong. The one right here with the bar, it's asking for the absolute maximum bending stress in the shaft. And the way we'll find that is the moment diagram, which I talked about at the start of the lecture. When we do that, one, we have the bar, we have the two forces happening, 400, 300, reaction at B, reaction at A. So we'll take the moment about A, and we'll get 400 times 12 plus 300 times 5 minus 30 by plus by plus u. So we get By is equal to 610. And then we can sum the forces in the y direction. And that'll give us that AY is equal to 90, which makes sense. 400 plus 300 minus 610 is 90. Now that we have those, we can construct our diagram. So we'll have several pieces 0 from x to 12. We'll have from 12 to 30. We'll have 30, 45. So the first piece is reaction of 90, distance x. That's all that's going on. So V will be equal to 90, and we sum the forces in y, and we sum the moment. Right here, we have the moment is equal to 90x. For the second piece, we have 90 V moment 400. This distance is 12. This distance is x. And we will have sum of the forces in the line. 400 minus 90 plus V. So V will be equal to negative 310. Sum of the moment. And sum of the moment. The moment is 400 minus 12. Oh, right. Minus 90x. Okay. And then for our last piece, as I mentioned before, it's just easier to analyze from the right to the left. So at the very end, we have this 300 force right here. This comes off. Our shear is in the opposite of this, our moment's in the opposite of this. And that's everything going on in that piece. So we sum the forces in the y direction. We get that V is equal to 300. And we sum the moment. And we get that is equal to 345 minus x. Now that we have our three pieces, we draw the graph. We are looking for the, to find the absolute maximum bending stress, we just need the max moment. We don't need the max shear. So I'm not going to bother drawing that. Just going to put the moment of x. And you can see from our equations, it's linear every single time. Starting with m90x, going from 0 to 12, it starts at 0, goes up to 124. No, that's not right. It's not 124. It's 1080. And we have our next piece right here. When we plug 12 into here, we get 1080, so we know we're at the right point. We plug in 30 into that, and we get much bigger. This is what it looks like. We'll be coming down to negative 4,500. And then we come back up to 0, and we do the last piece. There's our moment diagram. So our maximum moment is 4,500. So there's our end. And it's a circle, so it's perfectly symmetrical. Our C will be the radius, is 0.75 because they gave us a diameter of 1.5. And then our I is equal to 1/4 pi r to the 4th, which is just the equation for I. You plug all that in, looks like you do right there, and that gives you your max stress, your maximum bending stress. So what do you call it? You get that? Not too complicated, just tying all that together.
Where the 1/4 pi r to the 4 from?
That's the equation for I when you have a
Oh, it's a circular.
yeah. Yeah, it's a pipe through rod surgeon.
Another question is kind of unrelated, but when you integrate the shear to get the moment, what happens to plus c? I mean, it is indefinite, correct? I mean, you could just not include it, or is there such thing as this constant that you can add to that? I mean,
You could. Yeah, so C would be if there was a moment acting on the beam at that point itself.
okay.
So there was somewhere I saw, there's a problem from the previous section. You might have seen it. There was a beam that just had moments acting on it. When you integrate, that would be your C. But this doesn't have any actual just moments acting on it. It's only moments where the
That makes sense.
yeah. Just like, I don't know what the derivative of the shear would be, but it's kind of the same thing. If there was
So you would include the plus c and then add any moments to that and replace the c?
yeah,
Yeah.
but we don't have any, so the C is 0. You
So
won't,
have a diagram that both shear and moments and still get, use just integration and not have to do all of the math.
you could. The one thing I would want to be sure you did is remember that, like even if you integrate this to get this, you have to remember to change this range. Because when you're evaluating this, we're starting at 12, so when you're right here, this is not a part of it. But as soon as you move past to like 13 feet, this does have an effect. That's the one little thing I'd say to be careful about if you do choose to just integrate the shear to find the moment. Because if you just leave that as X, you're going to get way off. But you should be able to know or realize you're way off because when you plug the 12 in, you wouldn't end up at this point. You'd end up way up over here somewhere probably. So you also won't have any problems where you need to worry about that C in this class, as far as I'm concerned. That's it, not too bad. I just wanted to show that there was a correlation between the two things we've talked about today so far. And the last problem, as I said, I think it's a good exam question. We had multiple questions like that in my class on every exam.